This is the screencast for section 4.6, example 2. We're going to look at a rising hot air balloon, basically, and study its motion. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. So that's creating a visualization for me. So I'm going to draw a little picture. So at this point, all I know is that from the liftoff point, the rangefinder is 500 feet away. Then it says at the moment the rangefinder's elevation angle is pi over 4. Okay, wait a second. So this rangefinder, whatever that is, has an angle of pi over 4 radians. The angle is increasing at a rate of 0.14 radians per minute. Okay, so this is a change in the angle. So we'll call theta of t the angle of elevation of the rangefinder, which then means, as a side note, we don't have to define this, but d theta dt would be the change in the angle, and that would be 0.14 radians per minute. Then it says how fast is the hot air balloon rising at that moment. So how fast is the hot air balloon rising? Well, so here's the height, h of t. So I'm going to say that h of t is the height of the hot air balloon, which then means, as a side note, dh dt, the rate at the height is changing, is what we're looking for. So now I need to set up a basic relationship amongst the pieces I know or don't know. And I do get that, let's see, I have an angle, a right angle, and I have an opposite and an adjacent side. So I see a tangent equation here. So I have the tangent of theta of t equals the height divided by 500. So to see how all these relationships are changing together, I need to take the derivative, and remember that theta is a function of t and height is a function of t. So the derivative of tangent theta t is going to be secant squared theta of t, and then times d theta dt. And then this is 1/500th times the derivative of h, so that would be dh dt. So now I can plug in some numbers and solve. I'm essentially solving for dh dt, so I really could multiply both sides by 500 first. And then I get secant squared of, we said theta at that spot is pi over 4. And we said d theta dt, the rate that the angle is changing, is 0.14 radians per minute. And that will get us dh dt, which is about 140 feet per minute. So this hot air balloon is rising at 140 feet per minute. Then I'll try problem number 11. It says that a spherical balloon is inflated with helium at the rate of 100 pi cubic feet per minute. So that's the rate that the volume is changing. So I'm going to first define, let V of t equal the volume of the spherical balloon, which then implies that dV dt, the rate the volume is changing, is going to be 100 pi. Question A says, how fast is the balloon's radius increasing at the instant the radius is 5 feet? So we're looking for dr dt. This is implying that the radius is changing. Radius is also a function of t. So I'm going to say, let r of t equal the radius of the balloon. So now I need a basic setup of a relationship that will compare volume and radius of a sphere. So volume equals 4/3 pi r cubed. We've dealt with this one before, so now we're going to take the derivative. And we're trying to find how fast the balloon's radius is increasing. So we are finding dr dt. So I can divide both sides by 4 pi r squared and plug in dV dt's value, which is 100 pi cubic feet per minute. The volume is changing by 100 pi cubic feet per minute. And that is at the instant the radius is 5 feet. So the radius is changing at a rate of 1 foot per minute. Part B asks, how fast is the surface area increasing at that instant? So that instant is going to mean we're going to use some information from the previous problem. But it's asking how fast the surface area is increasing, so I need to define let S of t equal the surface area. And I know a formula for surface area, S of t equals 4 pi r squared, but r is a function of time, so I'm going to make that r of t squared because the radius is changing. So now we're going to take the derivative. ds dt equals, this will now be 8 pi r of t now to the first power, but then times the derivative of the function r, so dr dt. Now at this same instant, we are the radius is 5, and dr dt we have called 1. So we can find ds dt, how fast the area is increasing, the surface area is increasing, and I get that that's 40 pi square feet per minute.